Hello, I'm Prashant Nair, and I'm going to be talking about randomized RowSwap, mitigating row hammer by breaking spatial correlation between aggressor and victim rows. This was a collaborative effort between Georgia Tech and the University of British Columbia. Unfortunately, the first author, Gururaj, could not make it here due to visa issues. The second author could not travel because Canada is not permitting its students to travel during COVID. The third author could not be here due to personal reasons. Therefore, I would be presenting the paper. DRAM scaling has helped enable an increased DRAM capacity. Because of DRAM scaling, you can fit more cells in a given unit area. But this increased density of packing of cells actually increases cell interference. Because of the cell interference, access to a group of cells can actually influence its neighbors. For instance, if you have a DRAM with several rows of cells, accessing a row of cells to read or write can actually influence its neighboring rows of cells. And this interference is exhibited in the form of charge leakage. Now, if this were to happen infrequently, you can easily refresh these cells, say every 64 milliseconds, and replenish this charge. However, if this were to occur rapidly, you can actually cause an attack. And this was demonstrated in ISCA 2015. And this attack is called a row hammer attack, in which rows can be accessed rapidly and its neighbors can then be subject to self bit flips. The rapidly accessed rows are now called attacker rows or aggressor rows, and the victims are called victim rows. On the left-hand side, you have a small piece of code that can be used to trigger or orchestrate the row hammer attack. In fact, a software adversary can use this attack to flip a few bits in the page tables and gain kernel level privileges, and thereby take over the system. This was demonstrated by Seaborn and others in Black Hat 2015. In fact, row hammer attack has gained a lot of popularity even in drama and TV shows. For instance, Netflix has this show wherein the protagonist talks about a hacker that uses DRAM-based row hammer attacks to gain kernel level privileges. Now, given that this has become an important problem, vendors have tried techniques to mitigate the row hammer attack. One of the state-of-the-art techniques that is present in commercial chips is called the targeted row refresh. In a targeted row refresh, you have two mechanisms that are present. The first mechanism tracks aggressor rows, and the second mechanism issues mitigative action, in our case, a refresh to the victim rows. Unfortunately, targeted row refresh or TRR is broken. Two papers, Trespass and Blacksmith, actually showcase how one can break TRR trackers and thereby sort of overcome its defense. Right? Now, since the tracker itself is broken, we can replace the TRR tracker with some better tracker. For instance, you can have principal tracking using graphene, presented in Micro 2020, twice, CRA, and others. In this paper, in the randomized RowSwap, we actually use graphene trackers. Given the trackers are fixed, the next point of issue is the mitigative action. In fact, a few months ago, Google demonstrated the half double attack that uses this mitigative action to stage an attack. So we know that once the aggressor row attacks victim rows, those victim rows are issued mitigative refreshes. Now, these mitigative refreshes themselves can be aggressor-like events and can cause bit flips. So when an aggressor row issues mitigative refreshes to its neighbors, distance of 1 rows, those mitigations can be construed as an attack for the distance of 2 rows and can cause bit flips. Therefore, we need new mitigative action that is resilient to current and emerging attack patterns. And because DRAM vendors frequently change their mapping functions, and also because there are so many vendors out there, and because these modules keep getting replaced and changed in these systems, you preferably want to do this without knowing the internal DRAM mapping. To this end, our work proposes randomized RowSwap. The key difference between prior work and our work is that our work is an aggressor-focused mitigation technique. The key idea of our work is to remap aggressor rows and break the spatial correlation between the aggressor and their victim neighbors. So in this example, you have 2 victims for 1 aggressor row. After the aggressor is accessed T times, in this case represented by T activations, row X and the aggressor row are swapped. So now the aggressor row becomes row Y. Now, after that location is accessed T times, row Y and the aggressor row are swapped. So you keep doing this, and we, in our paper, have security guarantees that no row crosses the row hammer threshold within 64 milliseconds. Being the 64 milliseconds being the refresh window. Now, the key idea in randomized RowSwap of swapping rows relies on the fact that you can swap rows before the row hammer thresholds are crossed. And this swap frequency is determined by the value of T. The lower the value of T, the lower the swap threshold, the better the security. So you can swap frequently and thereby ensure that no one row would actually cross the row hammer threshold. So let's say the row hammer threshold is 4800, represented by TRH. You have to figure out what are the minimum number of activations in 64 milliseconds on a row for row hammer via any pattern. So we sort of present a security analysis here. And we consider single-sided, double-sided, and half-double attacks. Let's say that you have a row X, swapped with an aggressor, with the row X being chosen randomly. Now, the value of T should be chosen in such that if the aggressor were to randomly guess, because, well, the aggressor has no knowledge on the internal mappings, the aggressor should not be able to sort of pick up rows or group together rows such that eventually any one row would exceed the row hammer threshold. So we model this as a bucket and balls problem, wherein the random swaps are the balls and the number of rows in the memory in the bank are the buckets. So in our system, we had 128K rows in a bank. So we had 128K buckets, and we had balls that are determined by the value of T. So this table represents the value of T and the attack time. So if you were to swap at T equals TRH by 5, which is 600, then your attack time is 6.9 days. If you're going to swap with a value of T, which is TRH by 6, then your attack time increases to 3.8 years. And if you were to swap at a TRH of 7, then your attack time increases to 372 years. So the lower the value of T, the longer it takes to attack. The trade-off here is that if you present a very low value of T, then your overheads to actually move rows, swap rows, increases. So if you were to continuously remap aggressor rows, then we are able to sort of obtain principal security for years of attack. Now, how do you implement randomized RowSwap? To implement randomized RowSwap, we introduce two structures: the row indirection table and the hot row tracker. The hot row tracker was primarily inspired by graphene in Micro 2020. Both these structures are important. The row indirection table helps the randomized RowSwap framework determine the new location of the row that is being swapped. The hot row tracker helps the randomized RowSwap framework determine if an aggressor has crossed the threshold T. We implement these structures using a set associative logic, right? In this example, we show several sets and two ways. The problem with a set associative structure is that it is susceptible to various forms of attacks. For instance, you can have collision-based attacks, right? And you can actually have an attack wherein, let's say you have addresses A and B, address E comes in, A gets evicted, and this conflict causes certain rows, let's say A, to be expelled out of the structure, and we can actually lose tracking information for these rows. To overcome this, we leverage on a prior work that was presented at Usenix Security 21 called Mirage. Mirage leverages the power of two choices principle. In this principle, we add additional ways, multiple hashes, and load balancing such a way, and random replacement in such a way that when sort of an entry comes into these structures, we have two hashes to figure out where the entry will go. So in this case, the entry could go to your left-hand side, A and B, or towards the right-hand side in the same set as W. Because W's set has a lower load, E gets placed into the set where W is present. In fact, if you were to have 14 demand ways and 6 extra ways, thereby totaling to 20 ways, we get years of conflict-free installs. So here on the y-axis shows the number of conflict-free installs, and on the x-axis, we see the total number of ways per set. As you notice, adding just 6 extra ways enables us to get 10 to the power 30 conflict-free installs. Hence, by using multiple ways, multiple hashes, and load balancing and random replacement, we were able to avoid certain security pitfalls in tracking and enable randomized RowSwap to have strong and secure tracking. Given that you have secure tracking, these RRS structures are sized such that their overheads are low. For instance, the SRAM overheads for RIT and HRT combined is 45 KB per DRAM bank. And as we sort of simulate a DDR4-based system, we use 720 KB of SRAM per channel. Let us look at the performance impact of randomized RowSwap. On the left-hand side, you have the number of row swaps on the y-axis and different benchmarks or workloads on the x-axis. On average, we see less than 100 swaps per 64 milliseconds, which is very low, as each swap only takes 1.5 microseconds. On the right-hand side, the y-axis represents normalized performance, and the x-axis represents several workloads. On average, we see only a 0.4% slowdown. This means that the overheads of randomized RowSwap are very low and also does not require internal information about the DRAM. We compare randomized RowSwap with prior work, namely Blockhammer. Now, Blockhammer is another aggressor-focused mitigation method. In Blockhammer, the rate of the access of the aggressors is throttled as soon as they reach a blacklist point. As you see, the y-axis is the performance, and the x-axis are a set of benchmarks, and this is the S-curve for Blockhammer, and we compare it to randomized RowSwap. The randomized RowSwap incurs much lower worst-case slowdowns as compared to Blockhammer, as the mitigation is less expensive as compared to Blockhammer. Randomized RowSwap does not need to throttle the access for these aggressor rows. In fact, they just need to swap these aggressor rows to new locations. So the key takeaways to conclude is that we have introduced randomized RowSwap, which is a new aggressor-focused mitigation. It swaps aggressors with random destinations and successively remaps so that no row crosses the row hammer threshold. We show that randomized RowSwap incurs modest costs, 0.4% slowdown, 40 KB of SRAM per bank, while providing security against years of continuous attack. Third, it's resilient to newer attacks such as half-double, blacksmith, test pass, and potentially even future attacks that exploit complex patterns, as it breaks the spatial correlation between the aggressor and the victim rows.